Okay, continuing on, we're going to talk about what intervals or on what intervals are these functions continuous. So we start off with the square root of 1 minus x squared. We can see its graph here. And it is continuous on the closed interval from -1 to 1. Look at this one here. We have 1 over the square root of 1 minus x squared. Its graph looks like this, and it is continuous on the open interval from -1 to 1. And the reason for the difference is because note here that if x equals 1 or -1, then we get a function value of the square root of 0, which is 0, which is a defined point. So those are included on the interval of continuity. But in this case, we get a 0 here, which is the denominator. So we get a 0 of a denominator, which makes it not defined, and therefore it's only continuous here on the open interval from -1 to 1. And just to take a look at a trigonometric function, here we have tangent of x. It has vertical asymptotes at pi over 2, 3 pi over 2, and so on. So it is continuous only on the open interval from -pi over 2 to pi over 2, from pi over 2 to 3 pi over 2, and so on. Let's talk about the intermediate value theorem. This is the first named theorem that we need to know by name for the AP exam, so it's a very, very important one. The intermediate value theorem. There are 3 conditions for the intermediate value theorem. F is continuous on the closed interval. Notice it's the closed interval from A to B. F of A is not equal to F of B, and the value K is between F of A and F of B. If those conditions are found to be true, then there must exist some number C between A and B such that F of C is equal to K. So let's talk about what this means exactly. Let me put this under here. All right, so let's sketch a situation in which these 3 conditions are met. Okay, we have F is continuous on a closed interval, F of A is not equal to F of B. So let's work on these first 2. So let's just draw a random, kind of a generic sketch. If I have an x value here of A, and I have some function that's continuous, and here's my x value of B. So here I have it's continuous on the closed interval. Now condition 2 says f of A is not equal to f of B. That means these have different y values, which they do here. So we're good there. So we've met the first condition. Now we're going to pick some k value between f of A and f of B. So this is f of A here, and this is f of B here. So our k value has to be somewhere in this range here. So it doesn't matter where it is. Let's just pick a k value between f of A and f of B. All right. If these 3 conditions are met, then there has to exist some number C such that f of C equals k. So what does that mean? If this function value is k, then this x value is C. And so all the IVT tells us is if we have a continuous function on a closed interval, y values at each endpoint that are not equal to one another, and we have some k value in between those 2 function values, then there has to be some x value that corresponds to that point. It doesn't note here that it does not tell us what that C value is. We have to figure out some other way, in some cases, of finding that C value. But it does tell us that that C value exists. So one of the most common uses of the IVT is to find zeros of a function. So let's take a look at here. Use the IVT to show that f of x, we have x cubed plus 2x minus 1, has a 0 in the interval from 0 to 1. So again, we're not going to find out what that 0 is necessarily, but we're going to prove that it has a 0, that that function crosses the x-axis somewhere between x equals 0 and x equals 1. So in order to use the IVT, we have to justify its use. So we have to show that these three conditions are met, and if these three conditions are met, then we can make the conclusion using the IVT that f of x has a 0 between 0 and 1. So let's look. In this case, we have our a value is 0 and our b value is 1. So we're going to evaluate f of 0. We just plug that into the function, and the f of 0 value is -1. And when we plug in f of b, or f of 1, we evaluate that function, 2 cubed plus 2 times 2 minus 1, we get 2. Right. So we know that this function is continuous, so it meets the first condition. It's continuous, in this case it's continuous on the domain of all reals, but it certainly is continuous on the closed interval from 0 to 1. We've shown that f of 0 is not equal to f of 1. This is meeting the condition of f of a not equal to f of b. And we've also shown that our k value, we're looking for the 0, so the k value is 0. The k value is between -1 and 2. So we've met all three conditions for the IVT, and therefore we can apply the IVT, and what it tells us is, since f is continuous on the closed interval from 0 to 1 and the other conditions are met by the IVT, there must be a 0 on the interval. In other words, there must be a place where that function value equals 0 between x equals 0 and x equals 1.